All right, welcome back. So this is part 2. Cool. So where we left off is we were solving for Q's. So you know how to solve for Q now. Next, I wanted to emphasize again, equilibrium only works for heterogeneous mixtures. So we don't include solid and liquid. We do use pressure at equilibrium as well. But aqueous solutions and gas are only ones we use. So if I have a reaction like this, zinc 2 plus 2 GS. So the way we would write this is K equals, well, let's look at our products. We have this count. Again, this doesn't count because it's a solid, so we'll just put zinc 2 plus in there. And then we'll go to our reactants. Zinc solid doesn't count, so we're going to do Ag plus raised to the second, right? Because we have this coefficient of 2 up there. So that's how you write the K equation for that one. Again, no liquid/solids. Cool. Another example, maybe you have 2S plus 3H2O liquid goes to Fe2O3 solid. So for this one, K, we have a liquid, solid. So it looks like our reaction only favors, wait. Oh, I literally forgot one. Sorry, yeah. So plus 2H2 gas. So the only one we can do is H2 squared. So that means the only gas species is the one that is involved in equilibrium. Or in this case, we're only dealing with H2 gas. Right? Because solids and liquids don't count. So the rest are solid, the rest is H2 gas is in equilibrium. So next we're going to talk about manipulations with K. This is very important. So if you have a general equation, like we talked about or let me title this, manipulations with K. So if you have a general reaction like this, so K, we're going to write it as C squared, right, over A over B, products over reactants. This is a B and an A, like that. So we can also write it for the reverse reaction. Let's flip this reaction, because this is going in the forward. Like, it's kind of written in the forward. I know it says this way, but we can also write it as 2C gas goes to A gas plus B gas. And we can write a separate K equilibrium for the reverse reaction, right? So we can write it as A B over C squared. So that's something cool you can do. The reverse reaction, the K value is just going to be K to the negative of the reverse, or 1 over K for this one, right? Because we're just reversing it, the K value, or the reverse K value. We can also multiplied by a factor and see how that affects K. Let's do factor N. So if we have NAG plus NBG equilibrium with 2 NCG, same thing, it's just going to be C times 2 raised to the N, and then we have A to the N, B to the N, whatever N is, you're multiplying by that coefficient, right? It's just going to give you a K squared, whatever that factor is in this case. Next, we'll talk about adding reactions. You need to do this a lot. You're adding 2 reactions. And then we're going to calculate our K's, like what you do with K. This is kind of like Hess's law from Gen Chem 1. So if we have reaction 1, we have like AG plus BG in equilibrium with, let's say, 2CG. And we're going to add it with, let's say, 2CG in equilibrium with, TG plus EG. So we're going to add these reactions together. This is reaction 2. We can look for things you can cancel. In this case, we can cancel the 2 C's. And there's nothing else we can cancel. So on the right-hand side, or left-hand side, we have an A and a B. Equilibrium sign still stays. And it looks like we have a D and an E on this side. Plus E and G. And then these all have separate K equations, right? All of them. So for the first one, you can write it as K equals C squared over AB. That has an equal K equation. For the second one, we also have something similar. We have K equals DE raised to the C squared, right? And then this bottom one also has a separate K equation, right? We can write it as D times E raised to the AB, right? Products of reactive components. They all have separate K values. So how does that relate with just the general K value, right? This K value. Because this doesn't look like those. So whenever you're adding reactions together, you want to multiply their Ks. So it's a little different than Hess's law, but adding means multiplying. So mathematically, I can prove this. So if this is our K equation, how did we get from these two Ks right here to this K? So all you had to do is, let's label one K1. We'll start with reaction 1, C squared over A times B. We're going to multiply that by K2 times the second reaction, right? Oh. And which was D and E times C squared. Well, if you're multiplying, you can cancel these out, and you can multiply everything across. So this is gone, this is gone. We're left with this, and our K1s, which are just multiplied together, right? So it can be seen as K1 times K2 times, it's not K times that, but it's K equals this. So it's K is equal to, I don't know why it's not writing well. Okay, K, our overall K when we add the reaction is going to be K1 times K2, the two Ks together. And you're just going to multiply the reactions together, which is equal to D, concentration of D, concentration of E over A and B. See, now we have matching Ks. So whenever you're adding reactions, you just multiply their K values and you multiply the reaction out and you cancel out things that you don't need. So those are just some manipulations that you can do with K that you're going to be asked to do in some exams. Let's talk about last thing, equilibrium constant. So we have Kc, which is related to concentration, right? You can just label that whenever you're dealing. So later you're going to be dealing with concentrations, multiple types of concentrations, and different types of Ks. We have Kc, which represents the K equilibrium of concentration. We also have this one called Kp, which is going to be pressure, concentration related to pressure, which we're going to deal with soon. Later in the section, like next section, we have a lot of other Ks. We have lowercase Ka, we also have Kb, and we also have Ksp. And they're all different. There's a lot of Ks in this semester. But But Kp, but we wanted to do something. You're gonna have some problems dealing with K concentration and Kp pressure. So we wanted a way to relate this. So our formula to relate this is equal to Kp, or Kp equals our Kc value times R, which is your what was it? Your gas constant, which I'll write out again, times the temperature T raised to the N. So I'll tell you what all these mean. So let's start off with change in N. So this is going to be equal to the moles of gaseous products minus, remember the minus, moles of reactant. Moles of gas reactants. So it's the sum. So it's the final minus the initial, or just like the products minus the moles of the gaseous products minus the moles of the gaseous reactants. So that's going to be N. Remember, it's a subtraction. T is temperature in Kelvin always. Your R is going to be your gas constant, which is 0.08206 liters per time. It's atmospheres per mole K. Remember your units. We have moles, we have Kelvin, we got that so far. And your Kc is obviously your equilibrium constant, which you know how to calculate. And your Kp is what you're looking for, or you can manipulate this equation to do the opposite. Let's do just one quick problem involving this. So if we have a reaction, we have N2 gas plus 3H2 gas. We have 2NH3 gas. Let's say they give you like our Kc value is 9.60 at 300 degrees Celsius. Right? Perfect. So they're given this and they're asking for Kp. So how do we solve? So write out your equation. Make sure you have an equation list with you. So Kp is equal to Kc times RT raised to the change in N. Okay, so we're looking for Kp. Well, we're given our Kc, which is at 9.60. So we'll write that in. Our R constant is 0.08206 liters per atmosphere, or times atmosphere per mole K. Okay. I'm going to do another parenthesis times our temperature. So we have 300 degrees Celsius. We need to convert that to Kelvin. To go from Celsius to Kelvin, you have to add it by 278.15, I think. Or let me see, 278.15. Yeah, 278.15, I believe. But your K, that means when we convert it, it's going to be 573.15 K. So we'll write that in. 5.73.15 K. That's in Kelvin, extra parenthesis. And then we're raising all that to N. So what's N again? It's your moles of gaseous products minus your moles of gaseous reactants. So let's look at our moles. So it looks like here we have 3 plus 1, which is 4 on the reactants. Then we have 2. Remember, it's products minus reactants, so it's 2 minus 4. It's raised to the 2 minus 4. 2 minus 4 is -2. So let's rewrite this so it all makes sense. 6 times, let's just do 573.15. All right, and we're raised to the -2, right? It's 2 minus 4. Remember how I calculated that, right? We're summing up our moles and the reactants. We're summing up our moles and the products, and we're doing products minus reactants. 2 minus 4 is -2. So all you have to do is plug and chug, and you should get a Kp of 4.34 times 10 to the -3. Again, K is unitless, so that is how you solve for K pressure, or the equilibrium pressure. The next unit or next video, we'll be talking about the hardest concept probably of this unit that students always struggle with, which is ice tables, and then obviously Le Chatelier's principle, and then we'll probably move on to acid base after week 2 or week 4, I guess. But yeah, have a good day.